We have talked about, seen, and used the periodic table quite a bit so far throughout this course, and in this section we are going to dive a bit deeper into the construction of the table to understand the importance of why it was created this way. At a basic level, the periodic table is a fundamental organizational tool in chemistry, structuring elements into periods, which are horizontal rows, and groups, which are the vertical columns. This setup is based on increasing atomic number and recurring chemical properties. In addition to the general categories of periods and groups, we can also look at different elements within blocks, which correspond to the type of sublevel where an element's outermost or valence electrons are found. The periods are labeled 1 through 7 on the side of the table, so if we look at the elements within period 3, we could be referring to all of these boxes in the table. Groups are labeled 1 to 18, which are found on the top of the table. So if we were to look at the elements within group 17, we would be referencing all of these boxes. Taking a look at the blocks, the S block consists of group 1 and group 2, plus helium. The D block encompasses groups 3 through 12, the transition metals. The P block includes groups 3 through 18, excluding helium. And the F block, the inner transition metals, is usually shown separately at the bottom. It's important to note here that this section of the periodic table is pulled out primarily so it can fit better and be more readable on a piece of paper. The actual wide form of the periodic table looks like this, with the blocks highlighted like this. Notice that in this wider version, there are no individual group numbers for the F block elements. Lastly, in addition to these classifications, we can also group elements into metals, nonmetals, and metalloids, which we will cover in more detail later. Metals occupy the left and center of the table, primarily the S, D, and F blocks, and some P block elements. The nonmetals are located in the upper right side, the bulk of the P block plus hydrogen, and metalloids, or semimetals, form a stair-stepped line dividing the metals and nonmetals in the P block. Metals are typically shiny, conductive solids, nonmetals are dull, poor conductors with varied physical states, and metalloids exhibit properties intermediate between the two. Now that we know the different ways in which the periodic table can be viewed and dissected, let's talk about the importance behind all of these concepts. Let's start with talking about the significance of period number. This number represents the highest occupied principal energy level, N, for the elements in the row. This directly corresponds to the blocks that we looked at on the last slide, hinting at where valence electrons are found. So if we take a look at period 3 as an example, this would mean that all elements within this row have outermost electrons that occupy shells within the n equals 3 principal energy level, which we see here from the periodic table consists of the 3s orbital and the 3p orbitals. It's important to note here that the 3d orbitals are not part of this, even though they are technically in the shell of n equals 3. Taking a look at the periodic table, those 3d levels are filled with electrons in period 4, after the 4s orbitals are filled. We can take this knowledge of valence electrons and the structure of the periodic table and use it to figure out the electron configuration of any element. All we need to do is start at the very top left and go through the periods in order from left to right and top to bottom, counting each element and marking their electrons until we get to our desired element. Let's go through an example. Say we want to figure out the electron configuration for bromine, which is right here. We can set that as our target element. We start with hydrogen and move right, filling in electrons for the 1s orbital. We move down to the second period, fill in electrons for the 2s orbital, and then over to the 2p orbital, which has 6 boxes, so 6 electrons for 2p6. This takes us to period 3, which we fill in 2 electrons for 3s, and another 6 for 3p. We then drop down to period 4, we have 2 electrons for 4s, we then go through 10 electrons for the 3d sublevel, and then over to 4p, which we count 5 to get us to bromine. So, just using the periodic table, we can figure out the electron configuration of bromine, which is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. We can also take a look at the importance of the group numbers, which we have on the top as 1 through 18. Elements within the same group have a specific commonality, which is they have the same number of valence electrons, which are those electrons on the outermost shell. So as an example, all elements within group 2 have 2 valence electrons, and elements in group 16 have 6 valence electrons. When considering the main group elements, the standard definition of valence electrons excludes the d orbitals because they are considered core electrons in the context of main group element bonding. Here are the valence electron numbers for all of the main group elements. The last thing to know is that a few groups have specific names that scientists use to refer back to. Group 1 are the alkali metals, groups 3 through 11 are the transition elements, group 17 are the halogens, and group 18 are the noble gases. So when you hear these terms in your classroom, you should know exactly where to look on the periodic table to reference them. As we saw on the last slide, the elements within the periodic table are based on electron configurations of all of the elements. And because this is the case, there are trends and patterns within those electron configurations that we can identify and relate to the physical and chemical properties of every atom. This concept, that trends can be found across the periods and down groups within the periodic table, is called periodicity. There are a few key trends that you need to know about for the IB exam, which include atomic radius, ionic radius, ionization energy, electron affinity, and electronegativity. Let's break each one down and identify their trends using the different periodic tables that are provided to you in the data booklet that you can use when you are taking the exam. Let's start with atomic radius. The atomic radius of an atom is essentially the distance from the nucleus to the outer electron shell boundary, measured in picometers. This is measured by taking half the distance between the nuclei of two identical atoms bonded together. When we look at the periodic table, the radius decreases as you move from left to right across a period, such as from lithium to neon, because the increasing number of protons creates a stronger, effective nuclear charge that pulls the electron shells closer. Conversely, atomic radius increases as you move down a group, like the alkali metals, because each new row adds a completely new energy level, making the atom significantly larger. The same logic extends to the next concept of ionic radius, where cations, which are positive ions like sodium, are always smaller than their parent atoms because they lose an electron shell or experience less electron-electron repulsion, while anions, which are negative ions like chloride, are larger than their neutral counterparts due to increased repulsion in the valence shell. Bringing this back to the periodic table, groups 1, 2, and 13 generally form cations, and even though all of these are smaller than their non-ionic forms, we still see a trend of decreasing ionic radii from left to right when comparing these three groups. In addition, groups 16 and 17 tend to form anions, which are all larger than their non-ionic forms. But again, comparing their ionic states to each other, ionic radii still decreases as you move from left to right, from 15 to 17. Next, we can take a look at ionization energy, which is the energy required to remove an electron. The trend seen here is that ionization energy increases across a period and decreases down a group. For example, it is much harder to pull an electron from fluorine than from lithium, because fluorine's nucleus has a tighter grip on its electrons. Similarly, electron affinity, which is the energy change when an atom gains an electron, generally becomes more negative or more exothermic across a period, meaning elements like chlorine, quote-unquote, want electrons more than metals do, like iron here. We can also note that some elements do not have a value for electron affinity, as seen in this table, because they generally do not want electrons because they are stable. If we look at beryllium, 1s2, 2s2, it does not have a value shown, because adding an electron to the 2p orbital disrupts the stability, requiring energy, so its electron affinity is near zero or positive. Looking at nitrogen, it has a configuration of 1s2, 2s2, 2p3, which ends in a half-filled 2p subshell. This half-filled state is exceptionally stable, so adding an electron means putting it into an already occupied 2p orbital, causing repulsion and disrupting stability, leading to a near-zero electron affinity. Finally, electronegativity measures an atom's ability to attract shared electrons in a bond. Following the same trend, it peaks at the top right of the table and decreases as you move left and down. Using the Pauling scale, fluorine is the most electronegative element at 4.0, while cesium sits at the opposite end, in reference to stable isotope elements, with a value of roughly 0.8. Understanding these trends allows chemists to predict how elements will react, what types of bonds they will form, and why certain families of elements behave so similarly. Make sure to understand all of these for the exam, and remember that each periodic table shown in the video here is available to you in your data booklet while you are taking the IB chemistry test. You can mark them and annotate them as you see fit. Another important trend to note on the periodic table is with metallic character. which is defined by the ease with which an atom loses its outer electron. This is also inversely related to nonmetallic character, which is an element's tendency to gain or share electrons in chemical reactions. We can identify opposite sites of this trend by looking at groups 1 and 17 on the periodic table. In group 1, the alkali metals, metallic character increases as you move down the group, meaning that it becomes easier and easier for that single valence electron to be lost. This occurs because the valence electron is further from the nucleus and more shielded by inner electron shells, reducing the nuclear grip and making the atom more reactive. This is essentially outlining ionization energy, which decreases as you move down the group, again meaning the metallic character increases. This can be demonstrated when these metals react with water to form a metal hydroxide and hydrogen gas, following the general equation. The solid metal plus liquid water will yield a metal oxide plus hydrogen gas. The M represents the metal element from group 1. We can run this reaction with lithium and with potassium, and what we find is lithium produces a gentle fizz as the hydrogen gas is produced, but potassium reacts violently, often igniting the hydrogen produced. This is because the potassium has a higher metallic character, meaning it is highly reactive because they have a greater tendency to donate their single valence electron. Conversely, in group 17, the halogens, nonmetallic character decreases down the group. This means that as you move down the group, each element's ability to gain an electron decreases, aka it becomes harder to gain electrons as you move down. Since nonmetals react by gaining electrons, the increased atomic size makes it harder for the nucleus to attract an incoming electron. This shift is best seen in displacement reactions with halide ions, where the more reactive halogen, higher in the group, will kick out a less reactive halide ion from its salt. For example, chlorine will displace bromine ions because it has a stronger attraction for electrons, and in the same manner, fluorine will displace chlorine because of the same reason. So with this information, we can say that within group 1, cesium is the most reactive metal, it has the highest metallic character, and within group 17, iodine is the least reactive nonmetal, it has the lowest non-metallic character. There are no values for metallic and non-metallic character shown on the periodic table, so these are trends that you need to generally understand, and they heavily relate to ionization energy for metallic character and electronegativity for non-metallic character. The transition between metallic and non-metallic behavior that we discussed on the last slide is not a sudden switch, but a gradual continuum across the periodic table. This spectrum is most clearly observed in the chemical nature of element oxides, which are chemical compounds formed by taking an element from the periodic table and binding it with oxygen. When we do this and create many different oxides, their property of being defined as a Lewis base, which is a molecule that donates an electron pair, versus being a Lewis acid, which is a molecule that accepts an electron pair, changes. The basic idea is, as you move from left to right across a period, element oxides shift from forming basic oxides, which are ionic compounds of metals, to amphoteric oxides, exhibiting both basic and acidic properties, often seen in metalloids like aluminum, and finally to acidic oxides, covalent compounds of nonmetals. This trend reflects the increasing electronegativity and ionization energy of elements, with elements on the left side of the periodic table generally wanting to lose electrons, and elements on the right side of the periodic table generally wanting to gain electrons. These properties change how these metal oxides react with water. Let's look at a few examples. If we look at sodium in group 1, this can react with oxygen to create sodium oxide. Sodium oxide reacts with water to create sodium hydroxide. In this reaction, the sodium oxide, specifically the oxygen, donates an electron pair to the hydrogen in the water to form the hydroxide ions. This donation of electrons from the molecule classifies it as a Lewis base. If we take a look at a group 2 element, like calcium, it can also form calcium oxide. When calcium oxide reacts with water, the same thing occurs, where the oxygen donates its electrons to the hydrogen atoms in the water molecules, which form hydroxide ions. This donation of electron pairs again makes it a Lewis base. Moving further to the right of the table, we can take a look at aluminum oxide. This is a unique oxide molecule because it is amphoteric, meaning it can act as a Lewis acid or Lewis base dependent upon the molecules that are present for it to react with. For example, when aluminum oxide reacts with a strong acid like hydrochloric acid in water, it acts as a Lewis base by donating electrons from the oxygen to the hydrogen, which also accepts the protons, creating water and neutralizing the acid. When aluminum oxide reacts with a strong base in water, such as sodium hydroxide, it acts as a Lewis acid by the aluminum center accepting electron pairs from the hydroxide ion, forming sodium aluminate and water, which neutralizes the base. Lastly, we can move further to the right of the periodic table and look at sulfur dioxide. Sulfur dioxide can react with water and acts as a Lewis acid to form sulfurous acid. During this reaction, the sulfur atom accepts electrons from the oxygen atom in the water molecule, which makes it a Lewis acid. So, as we can see from our trends here, as we move from left to right across a period, the oxide molecules are basic for metals, to amphoteric, to acidic for nonmetals. This shift from basic to acidic oxides is a direct result of the decreasing metallic character of elements as you move across the periodic table. Before we move on to the last slide, there are two important points to make here with acidic nonmetal oxides and how we come in contact with them in our environment. The first one is with rainwater. Normally, rainwater is more acidic than regular water because of the presence of CO2 in the air. The carbon dioxide reacts with the rainwater and creates carbonic acid, lowering the pH to around 5.6. Which again is normal. But when other gaseous oxides enter the atmosphere that are further to the right on the periodic table than CO2, such as nitrogen oxides or sulfur dioxide, it creates conditions that are more acidic than usual with a pH of less than 5.6. Which we call acid rain. The end result of these molecules after they are oxidized is the creation of nitric acid and sulfuric acid within the rainwater, which are key contributors to acid rain. Sulfur dioxide and nitrogen oxides are produced both naturally through decomposition and volcanic eruptions, and unnaturally through industrial processes and the combustion of fossil fuels. Lastly, the increase in CO2 in the atmosphere also makes its way into ocean water, which reacts with the water to create carbonic acid. This carbonic acid can release hydrogen ions into the water, making it more acidic, and reduces the availability of naturally occurring carbonate ions to attach to calcium, which are now instead reacting with the extra hydrogen ions, making it difficult for animals to create shells and exoskeletons because calcium carbonate is important in that process. Last up for this video, you need to know about oxidation states. The oxidation state is a formal number assigned to an atom to represent the number of electrons it has effectively transferred or shared while forming a chemical bond. It is a hypothetical charge that an atom would possess if the compound were composed entirely of ions, assuming all electrons in the bond belong to the more electronegative element. So for example, if we have a molecule like methane, CH4, we know that this is a covalent compound, meaning its carbon and hydrogen atoms share electrons to form 4 strong covalent bonds. But when we look at the oxidation states of each element here, we are going to pretend that hypothetically, each bond is actually ionic and the electrons are completely transferred, which would form complete charges. If this was the case, the electrons will be pulled towards the more electronegative atom, which will be given a negative oxidation number, and the less electronegative elements that the electrons are being pulled away from are given a positive oxidation number. So in the case of CH4, 1 electron will be pulled away from each hydrogen atom, giving each one an oxidation number of +1, and the 4 total electrons will be pulled towards the central carbon atom, giving it an oxidation number of -4. Looking at ionic compounds, it's easy to assign an oxidation number because we do not need to pretend that ionic bonds are present. They are already there. So the oxidation state is identical to the actual ionic charge. For example, in sodium chloride, NaCl, sodium is assigned +1 and chlorine is assigned -1. In more complex polyatomic ions or neutral compounds, individual atoms are assigned states such that their sum equals the overall charge of the species. So for instance, in the sulfate ion, SO4 2-, each oxygen is -2 and sulfur is +6, totaling the -2 charge for the ion. The oxidation state of any element in its free or uncombined form is always 0. This is also true for structures with identical atoms, with equal electronegativity, meaning no atom can take electrons from another to create a charge imbalance. Since there is no net transfer or uneven sharing of electrons between identical atoms in molecules like O2, P4, or S8, the hypothetical charge remains 0. Oxidation states are important for chemical nomenclature, especially for naming oxyanions. There are 2 primary systems used for naming oxyanions, one using oxidation numbers and the other using generic or common names, both of which are acceptable for the IB exam. For example, in the case of nitrogen oxyanions, the ion with nitrogen in the +5 oxidation state, NO3-, is systematically named the nitrate 5 ion, but commonly known as nitrate. The ion with nitrogen in the lower +3 oxidation state, NO2-, is the nitrate 3 ion, conventionally named nitrite. Similarly, for sulfur oxyanions, SO4 2- has sulfur in the +6 state and is named sulfate 6, or simply sulfate, while SO3 2- has sulfur in the +4 state and is named sulfate 4, or sulfite. This dual naming convention allows chemists to choose the system that best suits their context. Again, you can use either method on the exam and should know what systematic names and common names refer to the same oxyanions.